Okay, so spatial data models are an important core integral concept for GIS, and we're going to break it down into 2 weeks. We're actually going to go a little bit different in order from the textbook. We're going to start out talking about spatial data models in general, and then we're going to cover raster data sets. Your book goes from vector data sets first into raster. Just timing wise, it works better to get raster done, and then we can talk all next week about vector data models, because that's probably the majority of what you'll do in GIS. Though raster data sets are getting a lot more usable these days. So this one's a rhetorical question. I didn't put it in the pair deck. How do we get from the real world to a digital representation from which we can extract the necessary information to solve a problem? So essentially, what does a digital representation of the world look like? Probably not exactly like the world, because the world is infinitely complex. And most of this GIS data collection has a purpose. It has limitations, or it has an overriding guidance structure behind it that helps make sure that the information that somebody pulls from that infinitely complex world meets the needs of the data collection. So that's going to look a little bit differently depending on what your goals are. So a spatial data model takes a real world complex system and represents it as a spatial object. And the end result of that representation can take a lot of different forms depending on what you're trying to achieve. So take a set of buildings like this. This straightforward, I'm going to map this region approach might just be to put points on your map, because you're never going to look at it in a small enough scale to see the objects. Or you might represent those buildings, or say these are neighboring states or country, you might represent them by their borders as lines. And then you may take that information and convert it into an area, which you can use to do area calculations. And that applies to other things as well. Cities, you'll often see, you'll have a city file that just has everything represented as points if you're trying to do an overall cartographic approach. Or if you're trying to manage a city, you probably have a boundary file for that city. Similarly for roads, most of the time you're going to see road maps as center lines, but if you're trying to design and construct a road, you're going to go out there and you're going to map the boundary of that road. So it's going to have a footprint, and you're going to use that for whatever your purpose is. So again, emphasizing that point, we do GIS for a reason, and that's to represent reality in some form. So to do, we have to simplify so that we can bring that information into our database in a manageable amount. Otherwise, obviously, we could go on for a year just mapping, or tens of years just mapping this tiny little area and representing all of the plants and buildings and animals, soil type, the people that live in the buildings, can all be represented in GIS depending on what your focus is. So you can see here, this person didn't really care about ballparks. I would say they left something important out if you're trying to manage your recreational facilities. But it looks like they're more interested in some underlying feature. It's probably not a physical feature, because physical features don't tend to have sharp edges. So without knowing the purpose of this map, it's hard to say what exactly they were trying to represent here, but it's clearly more to do with human constructed features than natural features. So when we do this simplification process, we take a real world entity and we represent it as a spatial object. I thought I had some questions on this. for you. Oh, not quite yet. So part of that process introduces a bias to your data, depending on what you're trying to achieve, depending on what your resources are in your data collection, but depending on the resolution of information available to you. If you had a data point for every single tree in here and you were trying to represent the foliage or coverage in an area, you would probably be able to make some really detailed specifications of like your percentage of vegetation type in this boundary. But the odds are that you probably just have an aerial photo or something that you can look at and see, okay, this area is mostly pine trees and this area is mostly deciduous trees. And so I'm just gonna draw some boundaries around that. So those decisions introduce bias into your data set, and then that's something important to keep in mind. And we'll talk a little bit more about some of those decision-making processes and how you can select your decision-making process so that you know your bias. So it's not that you're able to completely remove your bias, but you're using it intentionally for a purpose. Oops. So what are the consequences of data modeling? This is an actual question for you, not just a rhetorical question. In Pear Deck, it should be catching up with that slide now. And is it necessary? And why is it necessary? And feel free to pipe up if you have any questions. Oh, there it is. Sorry. So there we go. We have to simplify in order to make a data model. I can't remember now which dynasty it was, but there's a Chinese dynasty in which the emperor was very interested in surveying and mapping, and very interested in understanding his company's infrastructure. Unfortunately, the outcome of that interest and that desire to understand was developed into a modeling program, and that modeling program was to build a small-scale model of the country. And I think it might have started out with the imperial city. And when the emperor no longer felt that that model was sufficient to try to capture what he needed, he started another model that was built on a larger scale, and ended up putting a huge amount of resources into this modeling project, which was probably incredibly impressive and was certainly impressive for its time compared to the uses that we now put GIS to. It was trying to address a lot of the same goals, but it took up a lot of resources that then weren't available for this country he was trying to help. So we're very lucky to have GIS as a tool, and it has revolutionized management of so many different things that it's really hard to quantify what an impact it's had on our life for being something that so many people are very unaware of. So these are great answers. So here's what I want you to do is visualize this word picture. I'm not as lyrical probably as the professor who wrote this, but imagine standing on a hilltop. In front of you is a broad valley with a radiant autumn forest. Interspersed are homes, farmhouses, and a church. In the foreground is a large pasture, and next to it, a field of wheat. So, how would you represent that in GIS? Which entities would you focus on? So you can see here, there's a variety of different ways you can approach this. You can look at it from an elevation perspective. You're trying to map the underlying earth without the information that's on top of it, because it's going to detract from your understanding of the underlying earth. Your understanding of the soils that make up that area are going to affect your mapping if you care about soils, but it's not going to affect your mapping if what you're trying to do is represent all of the buildings in that area for FEMA when there's a hurricane that comes and wipes them out. So, oh, I thought there was more on that slide. There was. There's supposed to be more. Here we go. How would you represent them in GIS? Well, that's going to depend on what you're trying to represent. Obviously, if you're trying to represent elevation, there's a lot of different ways you can represent elevation. You can do some cool 3D modeling. You can do shading. You can color by elevation. You can work on contours. You can just show a point for interesting high features. Similarly for other structures. So. And then at what scale would you show this mind map that you have made? It probably depends on how you began to conceptualize that area. So if you're just looking at one little valley, you're probably going to use a large scale, and we'll talk about scale in a minute, and identify a lot more individual features than you might if you were trying to map an area that just happened to include this valley. So here's an actual image to go along with this description. As you can see, you can represent things in the near scale, or you can consider the fact that this valley probably extends well beyond what you can immediately see, and all of that could be mapped and represented. So one of the things that you can do with the GIS system is take each of these questions and each of these concepts as its own layer, and you don't have to pick and choose anymore. You can now have all of those things that we talked about and bring them into your GIS system. It's probably a mistake to try to put all of them on one map, but that's really the beauty of GIS, is that you have all of that information at your fingertips. You can manipulate it and interpret it and reinterpret it to your heart's content, and all that most people ever see is the map that comes out of it, but you get so much more understanding of your data than you ever would have if you hadn't come through the process. I found this representation interesting because it's probably the least sensical order that I could think of to represent these things. I find it interesting. You don't usually think of elevation as something that you would display on top of a political boundary. Obviously, you're not going to see a political boundary through most means of representing elevation, unless you turn it into contours or specific data points that you've isolated for a reason. Similarly with roads and soils, usually we consider soils underneath a road. So this is kind of an interesting perspective here, and I thought a good way to say, consider how you represent your data and how you layer it, because it does have an effect. All right, so when we use the term spatial data model, there's an underlying implication that you're connecting different pieces of information, right? This is not just a table of data. This is a table of data that relates to other data in other ways. So we've taken the real world, we've interpreted it into a data model that includes both an attribute table that at minimum identifies the objects that we're mapping and some critical information about those objects, and then the data model itself that we can represent in a lot of different ways. And then behind the scenes in that, there's a lot of information and a lot of decision making that goes into how those data models are built, which you may or may not ever need to interact with or know, but really comes into importance when you're designing a GIS system. And I don't mean writing software, I mean figuring out how you're going to implement your GIS system for whatever it is that you're trying to achieve. Understanding what's behind these data structures is really useful, because one of the things that becomes important is how much space is that data going to take. If you're representing this in the code that your computer can store, it's going to matter how much data you're going to collect, where you're going to store it, how you're going to deploy it. So all of that information becomes important. So right now for you, if you're working on the geomatics server, I forget, I think I said you had a 10 gigabyte limit. Maybe, I can't recall right now. I think the data set for this lab textbook is larger than that. So that's an important thing to consider. You're probably not going to want to store that in your personal data set, and we'll figure out some different strategies if we start running into data size limits there. One of the things I do, I think I showed you already, I deploy my GIS system through my Dropbox. So making sure that the data that I store on my Dropbox is within my size limits for that is really important. You can't do it with a run-of-the-mill free Dropbox. I happen to know someone who works there, and I babysat her as a child, so she owes me. But there's also a lot of different resources you can use for that. You can use your Google Drive. You have free storage with a Google Drive account for amounts of data that I didn't even imagine when I was starting to use a computer. And then, of course, a lot of alternatives like having a desktop drive or an external storage drive. So things to think about as you're building your geospatial library, because it's really nice to just do that once rather than over and over throughout your life. Okay, so the underlying important components of a spatial data model are obviously the spatial coordinates, and then the attribute information that made it important for you to collect those coordinates. So those are the primary components. There's a huge variety of different attribute data types that you can collect, but underlying that, there's really only like a set of, I think, 10 or 12 specific types, and we'll get into that, but they're basically composed of different types of numbers, different amounts of text that you can store. Some systems have a binary function where you can have a yes or no click, and that's all kind of driven by underlying database principles that we're not going to get into because that's pretty specific and out of the scope of this class. But essentially, you're going to need to understand the structure in which you're allowed to input attribute data into your system. So if your attribute text field has a 256 character limit, which is fairly common for database applications, then you should be prepared for that and understand that, because you're not going to be able to put something larger in there. And you can end up accidentally chopping off data that you didn't know you were doing, at which point it's probably not recoverable. So that's attributes in a nutshell. And then the coordinate data that allows us to position this. So we're going to get into coordinates and positioning systems in quite a bit more detail a little bit later in the class, but just as a general overview to make sure that you remember your elementary school geography. Hopefully you had, a good geography teacher at some point that talked to you about latitude and longitude and planar systems. So Can anybody tell me what I mean when I say a planar system? And I didn't put a pear deck on this, so you'll have to use your real words.
Is planar like a model of the Earth that is seen as flat, like on a sheet of paper?
Yeah, that's a good way to start it. And it's typically in an X and Y coordinate system, like a Cartesian system that you're probably familiar with from geometry classes. I say typically, not always, but that's the most common approach. And then, so what's the other important approach? Well, our world isn't flat, obviously. So the system that we're most familiar with is latitude and longitude. So hopefully you guys remember that from school. We're going to get into it probably in quite a bit more detail than you ever imagined later on. But some important things to understand about latitude and longitude is so we have arbitrarily divided the world up down the Greenwich Meridian and the equator, which is maybe a little less arbitrary, and assigned zones to those things. So we're most often in Alaska going to be working in the north latitude, west longitude zone. You'll notice as a teacher with some very detail-oriented is the word I like to use now, approach to things like this is that if you're going to say west longitude, you don't need to say that it's a -22. It's implied by the west. So something to keep in mind when you're filling out your homework, because that drives me nuts. But it's really important to indicate which zone of this Earth that we've chopped up into 4 pieces you're talking about when you're talking about latitude and longitude. Otherwise, when you start mapping things in Alaska and you use an east longitude, you'll end up in Russia. So that's always a good way to figure out why your data points aren't in Russia instead of Alaska. You forgot a sign somewhere. All right. So what that allows us to do then is take these real world entities that we're trying to represent as spatial objects and describe them in some way. So we start looking at objects and figuring out how we can represent them. And there's 2 different ways you can approach that. There's the object view, which is what we call vector data models. And you take each of those objects of interest to you and you assign them some sort of data format and collect your information about that. But then there's also all of these tools that allow us to collect really broad scale information about our work. So we have all these satellites collecting imagery, and we have really broad scale bathymetric mapping systems going out collecting huge amounts of data. And we don't want to represent that as discrete individual vector objects because it would be an overwhelming amount of information for the most part. So typically we represent that type of data as a raster data set. So you can think of that as either an aerial image or a thing we like to call a heat map because we often use heat colors to represent things from black to red with orange and yellow in between, or other types of visual continuous representation. And what I mean by continuous is even though we're cutting that up into little jumps, there's a continuum between this, oops, can't click, this end of our data spectrum up to this end of our data spectrum. It's not a discrete and interrupted boundary between those pieces of information. Oops. Don't like that pear deck hides part of my slide. It's not helpful. Okay. To figure out how to fix that. Sorry. So how would you represent a building in GIS? You maybe have some ideas about that from all the things that we've been kicking as dead horses. Right, so some of the most straightforward initial approaches to GIS would consider that a purely vector data set. But it doesn't necessarily have to be. So can you imagine, what, wrong one, how that might look if you tried to represent it as a raster? How do you turn a discrete object? Obviously, the building I'm standing in has walls and boundaries, and I've got property boundaries as a raster image. So here's some different approaches. This is a kind of a crude representation of a raster data set. And it starts to illustrate some of the issues that we run into when we try to represent real world objects as rasters, because those issues are pretty apparent when you talk about vector data sets. You're limited by the number of points you want to draw to connect your line to represent that object. Similarly, in a raster data set, if you take this line and you're trying to represent it as a raster, you're going to end up with this funky thing because of your limitation on these boxes that only allow you to draw in certain places. Your points can never be smaller than the size of the box, which obviously has some bias built in when you're interpreting points. And then, well, they happen to draw a rectangle that happens to be incredibly easy to represent as a raster, but what if that building was round? That representation would have some implications. Similarly, you can take a set of raster information and then try to represent it as a vector. So it's fairly common for us to take continuous data like elevation and try to break it down into something that we can draw on a map, or at least it used to be far more common than it is now, because now we have computers that can make beautiful pictures. Well, if you didn't want to paint your elevations onto your map, you had to represent them somehow. And typically what we did was contours. And then there's something kind of in between called a tin. If you can visualize this tin as a representation of elevation, I don't feel like it's the most straightforward tin I've ever seen, but they've added some shading to it. It looks like this is a ridge line, potentially. You have some valleys in here. And what you're doing is trying to break down different surfaces that represent this feature into little planes that you can connect. And then interpreting this into a data set that can be stored on a computer is really straightforward versus trying to do that with a smooth, continuous object that's infinitely complex.